I'm Kayvon Stassen. I'm representing the KELT team, the Kilodegree Extremely Little Telescope. We actually have a pair of identical robotic telescopes, one in Arizona and one in South Africa, monitoring 60% of the sky in both hemispheres, looking for transiting hot Jupiters around very bright stars in order to develop a small but important set of case study planets for detailed follow-up characterization. And here are just some screenshots showing you what some of our discovery light curves and follow-up radial velocities look like. And so we have a poster number 22, that basically serves as a mini atlas of the 8 very bright host stars with transiting hot Jupiters that we've discovered so far. And here you can see where they are in transit depth versus V magnitude space. As you can see, they're all way up there. These are particularly valuable, therefore, for detailed follow-up studies of the kinds that are listed in the bullets there. Because the transits are deep, they are amenable to detailed study as a function of wavelength, and because they're bright, that means that follow-up is easier with a lot of different resources. So what you'll see in our poster is a little bit of information about each of the planets. We welcome collaboration. We want to see these planets getting used for lots of different follow-up. And so if you're interested, check out the poster and be in touch, and we'll be happy to work together. Okay?
Thank you. Okay, so my name is Justine Lanier, and I'm working on the frequency of giant planets around low-mass stars. The survey that I'm studying is massive for M-dwarf statistical survey for direct imaging of massive exoplanets with NECO. This is a survey that has been led over 4 years with NECO, and it's composed of roughly 60 M-dwarfs, aged less than 120 million years and located at distances less than 65 parsecs, sorry. Here you have all the distribution in spectral types, distances, age, and magnitudes. And here you can see the mean probability of detection that I've calculated for this survey. You can see that we have probability of detection more than 50% for distances between 10 and 300 AUs. Next slide, please. Oh, okay. Okay, and thanks to these values, I've done a Bayesian analysis using a natural conjugate prior instead of using flat prior. And I found the fraction of massive stars that host at least one planet for these distances and masses, which is roughly 3.7%. And then I compared it with other survey, for example, A2F stars that have been a survey that have been led by Julien Rameau et al. In 2013. And here are the results. As you can see, there are less low mass, there are less planets, giant planets around low mass stars than around massive stars. So if you want to have more details about this study, come to see my poster, which is the number 23, and I have some flyers for you, so come. Thank you.
Hi, I'm Burak Doğruer from Ankara University. I will talk briefly about exoplanets in multiple stellar systems. For starting, there are planets, two types of orbits. There are planets orbiting just one component of the binary. This is the primary component of the binary. These are S-type orbits, and planets orbiting the center of mass of the binary system, P-type orbits. They are called circumbinary systems. Especially while the distribution of planets in wide systems more than 100 AU, the properties of the planets is identical to that of the planets around single stars, and but the characteristics of exoplanets in close binaries are significantly different than those around single stars. For example, the masses decrease with projected stellar separation, as you can see in this, and when we look at the mass distributions, here are the around single stars, around multiple stellar systems. Both power law and the log normal fit, power law is the dashed line and log normal fit is the continuous line. lead to the conclusion that the mass distribution of exoplanets in multiple stellar systems tend to have higher planetary masses. Next slide, please. And the P-type orbits, the first one is DP Leo, and most of them are discovered by the Kepler Space Telescope. Aside from Kepler, there have been planets discovered by the RV method and eclipse timing variations, O-C analysis. All known circumbinary planets are on long-term stable orbits, and two trends emerge in the orbital distribution. All planets reside close to the stability limit, and planets closer to the binary are dynamically unstable. And there are no claims of planets transiting very short period binaries, periods shorter than 5 days, despite the fact that Kepler discoveries, more than half of Kepler discoveries beyond this limit. Sorry. And the case of MRDL, this is, thank you.
Hi, I'm Rafael Millán-Gabet. I'm a project scientist for LBTI on the NASA side of things. So here's LBTI is one of the instruments installed at the Large Binocular Telescopes. Here it is in Mount Graham, Arizona. It's a NASA-funded project developed at the University of Arizona with Phil Hintz as the PI. It's a very versatile instrument with lots of operating modes. In the context of this conference, it addresses directly several observational aspects of planetary systems. In the mid-infrared, in the nulling mode, it's going to do a survey of exozodi emission. And at 3 to 5 microns, it's going to do an imaging survey of giant planets. Slightly older than other near-infrared surveys due to the longer wavelengths. So in terms of the presence at this workshop, I just point out Denis Defrère is going to give a talk tomorrow describing the instrument and all the modes and the science goals in detail. And then we have two posters, one describing how we select targets to most effectively inform the design of a future mission to image exo-Earths in the presence of noise due to this exozodiacal emission. And then there's another poster, P40, on how we are going to turn the observables from the LBTI nuller into this type of information on brightness due to exozodi emission. And that's it.
So I'm the last one between you and the lunch, so I will be quick. So my name is Julien Rameau. I'm about to finish my PhD at IPAG in France. So I'm interested in direct imaging of gas giants around stars which are massive, young, nearby, and dusty. So last year I detected a giant planet around the young and A-type star HD 95086. So remember this name. So HD 95b is a 5 Jupiter mass planet lying at a separation of 62 astronomical units. So follow-up observation with NACO, NIKI, and recently GPI showed us that the planet has extremely red colors, which suggests a high dust content into its atmospheres. The discovery also motivated other studies. So recently, a short observation and the modeling of the SCD of the star revealed the presence of a debris disk, which is made of two rings separated by a large cavity of about 50 astronomical units, and the planet might lie at the inner edge of the outer belt. So I would be happy to discuss more about this system if you want. And next slide, please. So as Justin told you, we also carried out a survey with NACO or DLT targeting 60 stars, which are analog to beta Pictoris. So we found a frequency of planet about 16% in this parameter range. And we also showed that the first generation of planet imagers, such as NACO or NIKI, were not sensitive to the population of planets formed by co-accretion, so these planets. But we also showed that the new generation of planet hunters, like Sphere and GPI, will be able to probe this system. And thank you.